All right, for 7C, we're going to talk about the law of large numbers, something that's very important to statistics and probability specifically. So this graphic is a little illustration of the law of large numbers that'll make a little more sense in a second in a different context. So the law of large numbers applies to a process for which the probability of an event A, we'll call that P of A, and the results of repeated trials are independent. And all it says is that if the process is repeated through many trials, so in math, whenever you see many trials or the long run, what they really mean is continued trials. So on and on indefinitely. The proportion of the trials in which event A occurs will be close to the probability P of A. The larger the number of trials, the closer the proportion should be to P of A. So I'll kind of put this into terms that aren't so dense. The idea is really, if something has a probability, like rolling a die in this case, and getting a 1. If it's a 6-sided die, the probability of getting a 1 is going to be P of getting a 1 is 1/6, right? But that doesn't mean that I should expect that after 6 rolls, exactly one of them is a 1, or after 12 rolls, 2 of them are guaranteed to be 1. What that does mean is that if I continue to roll, so here this is like 500 rolls, 1,000 rolls, up to 5,000 rolls. If I continue to roll, the proportion of rolls that are 1s will eventually approach 1/6, which is 0.167 as a decimal. So you can see in the long run, at first there's a lot of variability in the proportion of 1s, but as we continued more and more rolls in the long run, that proportion eventually begins to approach 1/6. So I can kind of show this to you in real time with another, hopefully simple example. So this is, what this is going to do is give me a frequency line chart of the proportion of heads and tails when I toss the coin. So I can set my number of tosses to, let's say, 1. I just want it to do 1 toss at a time. And I made this a fair coin, so the probability of getting heads is 0.5 or 1/2. So if I toss the coin, I got tails. So the proportion of heads I have right now is 0. Toss it again. I got heads. It's 1/2. We're at 0.5. I got heads again. Now 2 out of 3 of my tosses are heads, so 0.667 is my proportion of heads. And so the idea is that I'll continue to do this, and the proportion of heads will have some variability, but in the long run, we can kind of start to see it stabilize and approach the true probability, right? And so here, if I up my tosses to do 10 in a row, and so we kind of see as we put more and more tosses, we see the proportion of heads start to stabilize near 0.5. And that's all the law of large numbers is telling us, is that if something has a probability, a true probability, the more we participate in that chance process, the closer the proportion will be to that true probability. All right, so let's go back to our lecture here. Moving on. So let's do example 1. A roulette wheel has 38 numbers, 18 black numbers, 18 red, and the numbers 0 and 00 are in green. Assume that all possible outcomes, the 38 numbers, have an equal probability. What is the probability of getting a red number on any spin? So probability of red, well, we said that there are 38 total tiles and 18 of them are red. And so if we actually divide that out, it's going to come out to 0.474. So the probability of red is 0.474. All right. So if patrons in a casino spin the wheel 100,000 times, how many times could you expect a red number? So 100,000, it's a finite number, but it is a very large number. So what we would expect is for the law of large numbers to take effect. And since we just found that the true probability, or the theoretical probability rather, of getting a red is 0.474, we should expect that about 47.4% of patrons in the long run to get red. So what is 47.4 of 100,000? Well, we can just multiply 0.474 times that 100,000. And that's just going to tell us that about 47,400 of the spins should come up red. Great. So let's talk about this thing called expected value that leads us into. So to introduce it, consider two events, each with its own value and probability. We define expected value by taking the value for event 1 and multiplying it by event 1's probability, and then adding the value for event 2 and multiplying by event 2's probability. And again, this formula can be extended to any number of events by including more terms in the sum. So basically what it's saying is to find the expected value of some probability distribution, you take the outcome, multiply by its associated probability, and then add all those together. So I'll show you what I mean with an example. This is how the insurance business works based in probabilities. So an automobile insurance company sells an insurance policy with an annual premium of $200. So an annual premium, that's just what you have to pay every year to have this auto insurance. So you pay them $200 a year, and based on data from past claims, the company has calculated the following probabilities. So 1 in 50 policyholders will file a claim of $2,000. So that means the insurance company, they get in an accident or something, they file a claim, and the insurance company has to pay them out $2,000. 1 in 20 will file a claim of $1,000, and 1 in 10 will file a claim of $500. So each one of these has an outcome, a value, and an associated probability. And assuming that the policyholder could file any of the claims above, what is the expected value to the company for each policy sold? So expected value, let's see. Sometimes you'll see expected value referred to as E of X, just stands for expected value. So the expected value for the auto insurance company. So the premium you pay is positive money into them, and then when you file a claim, that's negative money that the company has to pay out to you. So first, we're going to account for the annual premium. Each customer pays $200. And we're going to add to that these expected values with the outcomes and their associated probability. So there's a 1 in 50 chance that a customer will file a $2,000 claim, which would be negative money for the company because they have to pay that out. And then I'll account for the others. So there's a 1 in 20 chance, so 1 in 20 is my probability, times the outcome that they have to pay out a $1,000 claim. And finally, there's a 1 in 10 chance, that they have to pay out a $500 claim. All right. And so now we're just going to go into our calculator, put that computation in. So I'll have 200, my premium, plus 1 in 50 times negative 2,000 plus 1 in 20 times negative 1,000 plus 1 in 10 times negative 500. Enter, and we end up with 60. So here's how we're going to interpret that. Go back to our slides. All right, so we got $60. So the way I might interpret that is, in the long run, so in that case, that means for many, many customers, the company can expect to earn an average of $60 per customer. All right, so now we know what the law of averages is, and we also know how to find expected value. So let's talk about some misinterpretations of these things that happen very, very commonly. And one of those is called the gambler's fallacy, which is the mistaken belief that a streak of bad luck makes a person due for a streak of good luck. What you have to remember is that these events are independent, and so their outcomes don't rely on each other, right? So a coin that you've tossed 10 times and has landed 9 heads and 1 tail isn't going to remember that on the next flip. It's independent, so it's equally likely still to be heads or tails. Casinos love to take advantage of this fallacy. Sportscasters also often get this wrong, and they'll refer to it as like the law of averages. And so in the sports world, like in baseball, you might hear an announcer talk about somebody who's had a bad streak of hitting and say they're due for a hit by a law of averages. There is no such thing as the law of averages. That's not a thing. There is a law of large numbers. All right. So let's kind of look at an example of this. So suppose you're playing the coin toss game in which you win $1 for heads and lose $1 for tails. After 100 tosses, you're $10 in the hole because you got 45 heads but 55 tails. So let's just work that out numbers wise, right? So that means 45 heads, you got paid $45, but 55 tails means you had to pay back $55, which when we subtract those still leaves us $10 in the hole, right? So in this case, the empirical probability, meaning the probability just by our little experiment of 100 tosses, is 0.45 for heads. Now, this is not the long run, right? The long run means continued tosses. So we're not like breaking the law of large numbers because we didn't get exactly 50-50 heads and tails. But remember what the law of large numbers does say is that as we continue trials, so as we continue flips, we should be getting closer to the true theoretical probability. So we keep playing the game, and with 1,000 tosses, you get 480 heads and 520 tails. Does that agree with the law of large numbers? Well, now our empirical probability of getting heads has gone from 0.45 to 480 out of 1,000, which is 0.48. So sure, it does agree with the law of large numbers because we are starting to get closer to the true theoretical probability of 0.5. Have we gained back any of our losses even though we're now approaching 0.5? Well, again, let's look at it this way. So 480 heads means we get paid $480. That's positive for us, but 520 tails means we have to pay back $520. When you subtract those, we're going to be in the hole $40. So no, we haven't won back any of our losses. In fact, you've had to pay out $30 more since you kept playing. And this is the type of thing that casinos rely on. So, one more little note, and this is just colloquial language. The house edge is generally the expected value to the casino in the case of a particular bet. So let's talk again about roulette, and let's look at the outcomes from the casino's point of view in roulette. So the simplest bet you can make in roulette is the red-black bet. So the outcomes there, let's make a little probability distribution, and the outcomes, the way this works is that you bet $1 and the casino either takes your dollar or on a red-black bet has to pay you your dollar plus an additional dollar back. So the two outcomes are, from the casino's point of view, the player can win or lose. And so there are values associated with that outcome. If the player wins, the casino loses $1. If the player loses, the casino wins $1. So the probabilities, remember, associated with the red-black bet, there was only 18 out of 38 that were red and 18 out of 38 that were black. So if you make a red-black bet, the probability that the player wins is exactly that, 18 out of 38. And remember, in a probability distribution, the probabilities have to add up to 1. So the only other outcome is that the player loses. Well, the probability of that happening is 20. So say you made a red bet. There's 18 red tiles out of 38, which would make you a winner. But to make you a loser, there are 20 tiles because there's the 18 blacks and remember the 2 greens. And if it lands on any of those, you lose. So notice if I add those two probabilities together, I do come out with 1, right? Okay, so now we're ready to calculate the expected value to the casino based on this probability distribution. So the expected value for the casino on any one spin of roulette is going to be the outcome value, so -1 times its probability, 18 out of 38, plus +1, that's the outcome if you lose for the casino, times 20 out of 38. All right, and all we have to do is add those together. And what we actually end up with, and you can verify this in your calculator, is about 0.05. So positive 5 cents in the casino's favor. And what that means, so the house edge is 5 cents per dollar bet. And that just means that in the long run, the house, meaning the casino, makes about an average of 5 cents on each dollar bet, specifically on this game, so on red black. Now that may not seem like a lot, but here's the way that is a lot. You can't actually bet $1 at a table. So they'll have minimum bets of like $5 or $10. And so multiply that 5 cents by, 10. And then the casino is the only one playing in the long run. Everybody else is playing in the short run. You're going to do a finite number of spins at the table. So the casino is guaranteed by the law of large numbers to end up making that 5 cents per dollar bet. So times that by millions of people, you know, a night or whatever it is, and that's a lot of money that you're guaranteed to make. All right, folks, so there's the problem set that's associated with this. Again, I will have answers posted to that. This is just for your own understanding of the material. You should be practicing these. But the assignment that I'm going to be collecting is going to be the Canvas quiz for this section, which will also be open note. So take it easy.